For lack of better terms or definition, I just titled this the scroll anatomy. Basically, what we're going to be talking about is the basics or the breakdown of how the scroll is put together inside. This is a very generic look at the basic scrolls. Again, I'm Don Gillis. I work under Educational Services. I've been with Emerson since July of 2017. Most of my career I spent working out of a truck as a technician. I'm a licensed journeyman, and I have a couple other things I'm a part of. Going on with the scroll here, the scroll technology, the first scroll was patented and issued in October 3rd of 1905. The first scroll production for us was in 1988. The shown on the screen is the patent issued in 1905 for the scroll. The patent scroll design was a rotary steam engine that you see on the screen there. Just a nice little fun fact there. Advantages of the scroll. Scroll advantages over there. Several advantages over the reciprocating compression technology, AC. Higher efficiency, has fewer moving parts. There is no valve losses, and it's a continuous flow. It's a smaller cyclical losses, and it's a better heat capacity. On the chart, you can see A and B. A and B are the AHR rating points. A is the system ER rating point, and B is the system SEER, rating point. And what does that mean to you? The ER is the energy efficient ratio. It's a ratio based on cooling energy and electrical energy. It is a ratio at a given operating point. I believe that operating point, if my memory serves me right, is like 95 degrees Fahrenheit and 80 degrees return air and somewhere around 50% relative humidity. SEER is just simply a seasonal energy efficient ratio. That's more of a moving target. You probably already know that. Just going to touch a little bit on the nomenclature for the models. Of course, the Z identifies that scroll. The second character is the application. So the application here, and then we would have the type of refrigerant that it was being used also, okay? This just shows your modulation. In this case, it's a digital uneven tandem. I want to point out the oil here. The reason I want to point out the oil here on this particular model is because notice the U here. There's a couple POEs up there stating what they're for. The U is one you'll see a lot, or in the future, I do anyways, with the up and coming availability of the R290 or the A3 refrigerant. The second to last three characters is going to be your motor protection, or pardon me, your motor description, then your motor protection, and then your electrical codes, what the hertz is and the volts and what have you. And last but not least, the last three is going to be your bill of materials. A little bit about the serial number. The first two characters, as you know, is the year. The third is the month of the year, ABC, January, February, March of 2003. At the last character in the L would be the Lebanon, Missouri plant. Pie charts, pie charts, pie charts. Here we got a pie chart. This is a pie chart. I think we looked at this the other day. These are updated continuously. This is just a pie chart showing you a basic scroll compressor teardown analysis, which we do on a regular basis in our 3-day courses. The things I want to touch on the most is note that the much higher return rate on the service compressors versus the OEM compressors. Again, the NFF is no fault found, and that's a huge number, a huge percentage here. I'm going to talk about a little bit why, the reasoning behind that is, some of the safety features that maybe a young technician or a seasoned technician isn't that familiar with. And that's really what I want to try to get out of this presentation the most, to be honest with you. And then we have the MNC, manufacturing nonconformance. That's on us. You'll see that that percentage is fairly small. It's smaller. It's actually smaller than this now. This is slightly dated, but not that much. The reason we have less on the scrolls is two reasons. Most of the scroll is done robotically, and again, there's less moving parts in there than we would have on a semi-hermetic. I'm going to walk through the cutaway here of the scroll. We're going to talk about low side pressure. Low side pressure is going to be anything under this blue area here called the muffler plate, or some people refer to it as the muffler cap. Okay, anything below that is going to be low suction pressure. Above that is going to be discharge pressure. We're going to talk about the mechanics, the compression, radial compliance. We're going to talk about the pressure balancing and axial compliance. High side pressure, again, is going to be this above the blue here, this muffler cap. This little device here, this is a deflector. You know how hot the top of a scroll gets. This actually is to prevent some of that heat from deflecting in different directions. And on the protection devices, we're going to talk about the internal pressure relief valve, or IPR, and then the TOD, the thermal operating disc. One is based on pressure, and the other one is based on temperature. And then we have our good old lubrication, and we'll talk heavily about that. This is a rough casting of the scroll. This is how we purchase the castings from our vendor. We have 2 or 3 different vendors. Notice the taps here, or I refer to them as dog ears sometimes. These will change during the machining process. The rough castings of the fixed and orbiting scrolls are placed together for the machining process and are mated for life. Okay, this happens to be the orbiting scroll, and you'll take notice here as we move along how much that changes. Here is the fixed scroll on the right and the orbiting scroll on the left. The orbiting obviously oscillates within the fixed scroll. It is the moving part. We call this the fixed scroll, and I usually use quotation signs when I'm talking to a class, but it does move vertically 1 millimeter, and we'll talk about that a little bit. I want to talk about the parts of the scroll set. On the left-hand side, the side of these walls, we refer to them as flanks. That's where we compress the gas up against each other internally inside. The very top of this is what we refer to as the tips. We do not use a tipping material like our competitors do, and I will talk a little bit more about that as we move along. This is the Oldham coupling, and the Oldham coupling sits at the bottom of the orbiting scroll, and it converts the rotating motion of the crankshaft to an orbiting motion and as the orbiting scroll. The Oldham coupling keeps the scrolls aligned and helps convert the rotation of the crankshaft in the orbiting motion. And these tabs, I put these in last night just to point the letters out. These tabs that are poking up here, back here, you can see the notches here. This is actually what those tabs are setting in that keeps them together. So this is the fixed scroll and then the orbiting scroll on the right-hand side. Okay. The scroll and how it works, we've got the low pressure gas coming in from the side as it turns on. We start unloaded, by the way. As we continue on, it works into the medium pressure cell, continuing on to the high pressure cell, and then eventually heading to the center discharge port, which, by the way, is the hottest point of the internally of that scroll compressor. Okay. This is going to be a video. There is no sound of this video. I'll talk a little bit about it. It's just going to show you the gas going through. You can see how it's coming. This is actually in the plant. This is running at 3,500 RPMs. It has a strobe light shooting at it, so you can actually see it moving. If not for that, you wouldn't be able to see it as slow as that was, obviously. You can see the gas coming into the discharge port and then leaving through the discharge port. Again, it starts on the low suction side, through it, comes on around, and through the discharge port. That's just a nice visual to show you how that gas comes through there. All right, moving forward here, we're going to talk about mechanics and radial compliance now. What is the radial compliance? The radial compliance is a side-to-side motion, if you will. Okay, they're talking about here this D shape inside the unloader bushing allows the scroll to radial unload. It separates horizontally when they encounter debris or some unusual operating condition. A radial compliance simply gives the scroll the ability to move radially, side to side. Centrifugal force throws the orbiting scroll against the fixed scroll, as we talked about earlier. So remember, the radial compliance is the side-by-side, and the axial compliance is our vertical. And then this is exaggerated slightly. This actually is just only 1 millimeter. The fixed scroll rises up, okay? But it protects the compressor from adverse conditions, okay? The axial compliance simply allows the fixed member to lift 1 millimeter if there is any kind of liquid flashing, for example, or a high compression ratio. The radial compliance allows the orbiting member to slide over horizontally, separating the pressure pockets at any high pressure gas at the top. And basically, we're going to use this little red dot here as a form of debris. It could be just a small little slug or some refrigerant, liquid refrigerant that got in there. And how that works is it separates the highest pressure from internally here. When it disengages, it actually pushes it back out only to flash off inside the scroll, okay, and starts back up. If you were gauged up to this, you would in fact see it. It's going to move your gauges obviously very slightly and then go back. Again, it's moving 3,500 RPMs, so it's moving very, very quick, and it'll happen very, very fast. This is another video. Hopefully, I can get it to play. This does have sound, and hopefully, I can get this to work for you.
During periods of cool weather, refrigerant can condense in the gas lines of HVAC systems, eventually migrating into the compressor. A key feature of the Copeland scroll compressor is its ability to handle liquid refrigerant with its compliant scroll design. During normal operation, radial contact between the two scrolls is held tight by centrifugal force, acting outward upon the orbiting scroll. Axial contact is maintained through positive pressure differential between the stationary and orbiting scrolls. In the event liquid refrigerant enters the scroll cavity, the radial and axial compliance allows the scrolls to separate, safely passing the liquid out of the scroll cavity without damaging the compressor. The Copeland scroll compressor design is comprised of mechanically compliant cast iron sealing surfaces. Inherent forces cause the scrolls to continuously seal against each other even as wear occurs. This wear-in versus wear-out design ensures high efficiencies and avoids the pitfalls of plastic tip seal designs, which often wear out prematurely, causing performance degradation and shorter compressor life.
All right, I got it to work. Successful. Okay, well, that was fun. Good video to show in class, and I'm sure you've seen it. If you haven't, you can find that on our YouTube channels Pressure balancing and axial compliance. What is the bleed port? It's located in the intermediate part of the pressure, the fixed scroll. It's a small hole through there. It allows the pressure to enter the intermediate pressure cavity. And I'll try to explain this the best I can. So the floating seal is typically sitting on this ledge here, okay? As it starts unloaded, the scroll starts unloaded, as it starts to pressurize, the gas starts to bleed through this port into this cavity area. And it does two things. One, it lifts this floating seal and butts it up against the muffler cap, closing off any possibility for that low suction to go back out. And two, it pushes down the fixed scroll to engage our tips here, okay? Again, we don't use any kind of a sealant material. It's all oil and metal to metal, okay? Cast iron to cast iron, okay? And that's how that works, which I think is really, really cool. It's pretty neat engineering. Here's a shot of the floating seal. You're looking down at the fixed scroll here. These are the sleeve guides that let it go up that 1 millimeter up and down. Here is our floating seal setting down on the top of that fixed scroll, okay? That's a TOD down there in the center of the scroll you're looking at. And here's the actual floating seal by itself. There's a gasket on the outside and the gasket on the inside. I always stay around when we're giving tours to contractors and watch this process. It is very neat, okay? You've got a cast iron top. There is a aluminum bottom. It's like riveted together. Really, really neat. The neat thing about that machine, again, to get into robotics, is they have cameras set up. And if everything isn't lined in just perfectly, the machine will not press it together. Pressure balancing axial. The sleeve guides, again, what we just looked at, helps hold the fixed scroll in position and permits the scroll to move axially or up and down using the sleeve guides, okay? This is the right side of what we just looked at over here. Here's where we pressurize, moving that floating seal up, okay? When we push down, we've got that 1 millimeter. You can see this bolt has like a washer connected to it, all right? And there's a sleeve guide in the center of it, allows it to stop. This is the high side pressure, again, above the muffler cap. Everything above that yellow line is our muffler cap, okay? It's contained by the compressor's top cap, muffler plate, wear disc, and the fixed scroll. You can see this shooting up here. As the floating seal butts up against the muffler cap, is forced against the muffler plate, the metal seal of it, if you will, separates the high side from the low side, as we talked about earlier. The high pressure pocket is compressed of gas, passes through this center of the floating seal and the muffler plate into the top cap above. Again, this is a deflector here. And if you've ever touched the top of a scroll compressor after it was running, you probably wouldn't do it a second time. This is an IPR, by the way. We're going to talk a little bit about that here shortly. This is simply a check valve on the left-hand side leaving the discharge port. What it does is prevents discharge pressure from flowing back into the compressor during the shutdown cycle or shutdown. It helps to reduce shutdown noise. It also prevents re-expansion gas coming back into it. We talked a little bit about re-expansion gas the other day, getting in our underneath our reed valves and what have you. This is just showing you the scroll. I'm going to use the left here first, okay? You can see the rotor turning around. The crankshaft is straight with an offset at the top of the orbiting motion of the scroll. There is counterweights at the top and the bottom, okay, due to the offset of the scroll. And the rotor turns again approximately 3,500 RPMs. And the bearing at the bottom, take notice, should always be submerged in oil, all right? And you can see here, the violet colored piece here is our Oldham coupling. The orbiting scroll is moving. There's that bushing I talked about earlier, that V-shaped bushing, that unloader bushing, okay? And there is a piece of Swedish steel in there that I didn't mention, I apologize. It allows that to go left to right. In fact, I tell you what, I'm gonna see if I want to go back and look at that one more time. I forgot to mention this. This is very, very important, and I'm sorry. This piece of Swedish steel here is put in there. It naturally wants to go straight. This allows that left to right motion. It gives it that spring, if you will. So that's our radial compliance. That's kind of the secret sauce behind that. And I do apologize that I missed that. Okay. And there's that bushing we just talked about. Again, the violet here, or the teal, if you will, is that floating seal. You can see the blue arrows going down indicating our gas. It is refrigerant cooled, so it's coming across that motor, picking up that heat and moving it out to the discharge line. We'll talk a little bit about lubrication here. Lubrication. 4 points we're going to touch on here. The lower bearing and the main bearing work together to maintain a gap between the rotor and the stator motor. You can see the straddle bearing at the very top of here, what the orbiting scroll sits on. You have the drive bearing or the unloader bushing we just talked about. And then we have the main bearing here, and then that lower bearing we just talked about. Lubrication is provided through a hollow hole through the crankshaft here, and flood back is not easily damaging to the scroll set, but lack of lubrication is a big problem. Example of flood back would be like poor airflow across the evaporator, for example, or the TXV is not is starving or letting too much refrigerant loose. Lubrication, I'm going to take these one at a time. Here's the shaft I just talked about. It is offset. Notice this lobe on offset of the center of this that allows that orbiting motion for our orbiting scroll, okay? Here is just a close-up breakdown of the lower bearing assembly that we talked about, submerged in oil all the time. And then at the very top in the middle, we have our oil flinger. I'm going to use this one at the bottom. It's a little bit better picture. I don't know if you can see these two little flingers here. They're almost like little rudders or paddles, if you will, okay? And on the right here is our shaft. And you can't see it with the naked eye, but it's drilled out at a slight angle. And you can see where it's drilled out on the sides here where we're lubricating the bearings, okay? So again, we start unloaded, all right? And the shaft is sitting down here in this oil. As it fires up that 3,500 RPMs, those little flingers are rotors, if you will. The hole at the bottom of the shaft is smaller than the hole at the top, okay? So as it starts up, the oil naturally wants to draw up, causing like a Venturi effect, if you will. The speed of the scroll itself moving 3,500 RPMs causes a centrifugal force, almost like a barber pole, if you will, okay? And candy canes up there to the top of it. Again, that's just my terminology, bear with me. This is that straddle bearing here at the top. This is that loader bushing I was talking about. As the oil continues to move up the oil riser, it will exit out the top of the crank drive pins. Notice this hole over here. This is how the oil would drill back out, down. These are those sleeve guides I was talking about earlier, okay? Some models use an oil drain and some use the oil tube to help drain the oil between the stator and the rotor. And other models have just eliminated the tube, letting the oil just drain out the hole like you see in the picture here. We're going to talk a little bit about protection now. I'm so used to stopping after each slide and asking if there's any questions, so bear with me. I'm trying to get used to teaching like this. So the protection here, we're going to talk about the TOD. Again, it's the operating or the temperature operating disc, okay? The IPR is the internal pressure relief. It's based on pressure. This one is based on temperature, the thermal operating disc. And then we have the floating seal. And the floating seal, as you already saw, serves one purpose, but it also acts as a safety device for another purpose. And then we have our motor protector, okay? The IPR and the TOD direct hot gas on the motor protector and shut down the motor, okay? And the floating seal protects against high compression ratio and allows the discharge gas back to the suction side as it drops down. We'll talk a little more about that. Remember that high compression ratio is the #1 reason for high heat, and heat is the #1 killer of compressors. We talked about this the other day. So this is our scroll compressor safety device. What is this protector? The protector is attached and wired in series with the stator. The protector opens the circuit in the event of high amperage or high temperature conditions. So the overload might be open if someone walks up to it with their voltmeter and checks it out. This falls in that NF category on that pie chart we talked about earlier. A technician, whether it's a seasoned technician or someone that's green, just new in the field, comes out with his voltmeter, and the overload might be open and not the windings. So they're going to have to let this cool for a while. And the motor protector, as I said earlier, is wired in series. It opens the circuit on high amperage and high temperatures again. Some people will run water over this. I know we used to do that a lot when I was out in the field. Supermarket guys, to expedite the cooling effect, will pack it in ice to bring it down. So to take a look at this IPR, this is, first of all, it's a pressure difference from the high side to the low side. Again, above the yellow here, the muffler cap, is our high discharge pressure. Okay, we have low suction pressure down here. Below, it is a pressure differential. In the event that the high side pressure exceeds the normal operating conditions, the muffler plate will open and releasing the motor protecting, tripping the protector. It works again on pressure differential. So the pressure, internal pressure relief valve or IPR on a normal refrigerant, it would be somewhere between 375 PSI to 450. 410A on R410A, it's somewhere around 625. The high pressure side of the muffler plate will open. Again, it will allow the gas to come down on our protecting device, okay? So for example, if somebody forgot to open the high side or the service port on the liquid line, for example, and I know I've done that before when I first start out. You think you have everything opened up, and all of a sudden you don't. And this just keeps it from turning into a giant hand grenade, really, and cause catastrophic danger or injury. Here's the TOD. Again, the TOD is another protective device. It is a bimetal, sort of like the ASTP we talked about the other day, and it opens on high discharge temperature. So when that gets to a certain heat, that bimetal, those two metals react differently, and it opens up, okay? And then pouring the direct hot gas or shooting that direct hot gas to the protector to shut the compressor down. The device prevents the orbiting scroll and fixed scrolls from overheating, and also, again, it directs the hot gas towards that motor. So this opens up. You can see this fixed scroll has a little channel or a hole bored through it. You can't really tell it all that well because it's a dark on dark here, but this is actually 90 down, and it's shooting down on that safety device we talked about earlier. Floating seal and the compression ratio. So we talked the other day about a good compression ratio for air conditioning is somewhere around 3 to 1, medium temperature 5 to 1, low temperature 10 to 1, just roughly. None of that's sketched in stone. So after I told you all that, what that's good at, on the left-hand side is showing a loaded scroll, okay? We have that bleed port coming up there, causing that floating seal to go up, okay? What they're saying is here, the left is loaded and the right is unloaded. In air conditioning mode, as long as it stays less than 11 to 1 compression ratio, the floating seal will stay up. As soon as it gets above 11 to 1 compression ratio, this cavity in here gets weaker and weaker and doesn't have enough pressure to keep this floating seal butted up against that muffler cap. So it therefore drops, pushing that low suction gas back down, okay, and stopping it from running. Now, do we want you to run 11 to 1? Obviously not. I said a normal would be somewhere around 3 to 1. This would definitely be outside the envelope, okay? Refrigerant, same thing. Lower than 26 to 1, we're still good. This is what it's tested for. Above 26 to 1, it will fall down. Again, lack of pressure in this intermediate area here, okay? Anti-rotation device, it's located in the fixed scroll. It works like a check valve, preventing high side gas to return through the scroll. So the way this works is, in normal operation, as it's discharging the gas through the muffler cap, I'm gonna act as if this is use it like a thimble, if you will. It slides up, allowing the gas to come around and go through the discharge in the upper part of the muffler cap. Okay. On shutdown, it takes the least path of resistance and comes back through the center, pushing this this USD down, blocking that off for any possibility of any re-expansion gas, okay? This is the labeled, the scroll components labeled. I'm going to give you just a second or two to think this through on your own. This is normally where I would stop in class and have them either work together or by themselves, okay? So we'll walk through this. Hopefully you'll remember what I just explained to you. And since I can't ask you what A is, I'm just going to tell you the A, again, the blue here is going to be our muffler plate. That is separates the high side to the low side. The B is going to be our floating seal, okay? Then we have C. Hopefully you knew that was our fixed scroll on top, okay? The D is the orbiting scroll at the bottom. That's the oscillating motion, okay? And then we have E. That's our Oldham coupling, kind of our secret sauce. Between that and the floating seal, I found that really fascinating when I got here a few years ago and had to learn all of this. I found those two pieces, and the scroll set itself is fascinating, but I found the floating seal and the floating seal and the Oldham coupling to be kind of the secret sauce behind everything. The F obviously is our crankshaft, and then G is the windings, the rotor or the stator, and for the purpose of all of them, okay? I'm going to touch on commercial AC slightly here. This is just a snapshot of the commercial compressors and modulation technology comparison. At the top, we have our fixed scroll, then our two-stage, our digital, our variable speed, and our multims, tandems or trios, okay? Everyone knows what the fixed scroll is, and you can see what sizes they come in. They range from 2 to 40. This is 2 to 10 on the two-stage, 3 to 15 on the digital, which happens to be my favorite compressor to talk about. I love talking about digital compressors. The variable speed is somewhere around 2 to 15 horsepower, and then 3 to 120 here on the tandem. That's very versatile. Okay, and then you can see how it shines in the part loaded, full loaded, and the comfort issue. Notice the variable in the comfort issue can't be touched. Okay, I think as time moves on for homes, anyways, in your residential, you'll see more and more variable speed as it becomes more common, and things become the EPA and different things start to change for efficiencies. Commercial scroll. Some of the things you'll see on the commercial scroll will be a disc check valve. You'll have a high pressure tap. There is no internal pressure relief. You'll have to have an outside thermostat. There's no bimetal thermal disc inside here, okay? There is a direct suction and a motor cover. A dirt trap is nothing more than magnets here at the bottom collecting any kind of film that could possibly come off of our scroll set. By the way, unlike our competitors, and I don't like to sling mud, I never did as a contractor, but our scrolls actually get more efficient as they run in time because we don't have that tipping material that we use, which I think is pretty cool. It actually gets more efficient as it runs, so it doesn't run out. Then we have a line brake protector here again. And then something you're going to see as these shells get larger, you're going to start to see a motor spacer here. Temperature protection, the discharge line temp thermostat, again, required to cut off the compressor somewhere around 2 to 220, 50-degree differential. You need to insulate that thermostat. So in other words, if one's there and you replace the compressor, they have to make sure they don't just leave that flinging in the air there. It has to go back on that discharge line, and that is major. You have to remember that. You mount that 7 inches from the outlet tube or 5 inches from the valve. It is required on 7 to 15-ton models for all refrigeration applications and AC heat pump applications. Ensure that that thermostat is placed back in that correct position and insulated. If the compressor doesn't have the built-in protection, we must have it externally. This just shows you another type of a check valve, if you will. This is referred to as the floating valve, and basically it's like a flat washer, if you will. When the gas starts to come back, this is that floating seal, by the way. This check valve comes down. It covers up these holes here in the floating seal and blocks off any opportunity for re-expansion gas back in the scroll set. Okay, so keeps it as efficient as possible. Remember, re-expansion gas is a bad thing. It's gas that we've already pressurized. We paid to do that already, and we're actually pumping it over again. So you'll see these check valves stopping any gas coming back in. The larger scrolls will have a larger area in the top cab, obviously. So the washer, instead of the check valve being in the discharge line itself, you might have two of these. You might have one up above. The washer is to use to prevent a rush of discharge gas back through the scroll set on shutdown. And here is the advanced scroll temperature protection, or the ASTP, that we talked about the other day. I think that was Friday. We have a tandem here and then a single here. Again, we're looking for that sticker on the outside. This, again, is a bimetal safety device. Again, like the TOD, it goes off somewhere around 270, 275. Again, you'll notice with all of our safety devices internally, they all go right underneath that 300 degrees. That 300 degrees is important to know because that's when our oil starts to break down. This just shows the close-up of that advanced scroll temperature protection, or the ASTP. This is just blown up from what we talked about earlier. That bimetal is closed here. Everything's good. If it gets too hot or it hits that 275, it opens up down here, allowing that gas to come down through here, through the fixed scroll, releasing that and not allowing that floating seal to stay up in that pressure cavity. Remember, we talked about that earlier. It's very, very similar, almost identical to that TOD that's bored out in the fixed scroll. It's a proactive approach to discharge temperature protection, okay? Remember the sticker, the decal. So if you're helping somebody troubleshooting something over the phone, it might be running but not pumping. You want to make sure they're not dealing with an ASTP. And again, misdiagnosed falls under that NFF on our pie chart we talked about earlier. And I believe, Julie, that's all I have for this part of it. I was fearful to get into any more than that because it would run too long. I went a little faster than I thought I was going to, but we still got her in. Give us some extra time.
Yeah, that's perfectly fine. I have not seen any questions come through, but we did have quite an audience out there today.
Oh, good.
So I appreciate your time once again. For those of you that are on the call, I know I've been inundating you all with meeting notices. I did just send out a recurring meeting notice for these daily trainings, and I'm working on getting the full schedule together for what we're going to train on over the next couple of weeks. So hopefully before we start the training session tomorrow, I can run through that so that everybody can forward the meeting notices in advance. So no additional questions have come in. Don, once again, thank you for your time.
Thank you. Thanks, everyone.
When we reconvene here in about 20 minutes, we're going to go over a couple of topics from the daily update side, from the product side. I'm going to have Mike Williams talk about the Modulode to Discus Digital, the cycle timer, the digital timer conversion kit that's available. And then I will go over an update over the Reynosa facility. For those of you that may or may not know, the Mexican government did come in and suspend operations late last week for our plant in Reynosa. So I'm going to go over a couple of things related to that, and that will be the 12:30 call. So everybody go grab some lunch. For those of you on the West Coast, go grab another cup of coffee, and we'll talk to you shortly.
Bye.
Thank you. Bye-bye.
Thanks, Jim.